You know, in the Kubernetes world, we talk all the time about services that are meant to run forever. But what about all the work that's actually supposed to stop? Think about it. A database migration, a nightly backup, or a one-off data processing task. These things need to start, do their job, and then, crucially, finish. Well, welcome to the world of jobs and cron jobs. It's a totally different way of thinking.
So, here's our game plan. First, we're going to completely flip our thinking from always on to run to completion. Then, we'll dive into the basic job object and figure out how to scale it out with some powerful parallel processing patterns. After that, we'll put it all on autopilot with cron jobs. And finally, we'll get into the really important stuff, how to handle failures gracefully and how to keep your cluster nice and tidy.
All right, first things first, we have to do a little mental reset. Pretty much everything you've learned so far about keeping pods alive at all costs, we're going to turn that right on its head. For a Java, the goal isn't to live forever. The goal is to die a happy, successful death. And that is the core idea we need to get our heads around.
Okay, this is where it gets really interesting. It's all about flipping the logic. Just look at that pod exit row. For deployment, if a pod exits with code 0, which everywhere else in the universe means success, the controller sees that as a failure. Its job is to keep things available, so it immediately spins up a new pod. But for a job, that same exit code is a victory. It's the whole point. The controller high-fives it and says, "My work here is done."
And this quote just nails it, right? The replica set, which powers deployments, is basically a bodyguard, fighting to keep its pods alive no matter what. The job controller, though, is more like a mission director. Its entire purpose is to guide its pods to a successful conclusion. Their missions are polar opposites.
Okay, so let's get our hands dirty and look at the job resource itself. This is our fundamental building block for any kind of batch workload, any task that needs to run once and then stop.
And this is the absolute key. The job controller isn't constantly asking, "Hey, are my pods up and running?" No, it's asking how many of my pods have finished successfully. Think of it less like a doctor checking a pulse and more like a coach counting successful laps. It's all about tracking completions, not just availability.
And the life cycle? It's actually beautifully simple. You create the job, the controller sees it and launches the pods you asked for. It then just sits back and watches, ticking a box for every pod that succeeds. And as soon as that count hits the target you set, bam, the job is done. It's a nice, clean, predictable process.
Okay, but what happens when things go wrong? Because they always do, right? Your restart policy is a huge decision point. If you choose on failure, Kubernetes will try to restart the container right there, inside the same pod. This is great if your application has a high startup cost or if it can save its state. But if you choose never, Kubernetes creates a brand new, squeaky clean pod for every single retry. This is perfect for stateless tasks or when you really need to look at the logs of a failed pod without it being wiped.
All right, running a single task is cool and all, but where's the real power? It's in going massive. Let's look at how jobs let us unlock some serious parallel processing capabilities.
I mean, this is the classic problem, right? You've got this mountain of work, thousands of images to crunch, hundreds of video frames to render. You just can't do it one by one. It would take forever. You have to divide and conquer. And luckily, Kubernetes jobs give us a few fantastic patterns to do exactly that.
So think of this table as your playbook. A simple database migration, that's a single-shot job. But the real magic happens with the fixed completion pattern. You tell Kubernetes two numbers: completions, which is the total number of tasks you need to finish, and parallelism, which is how many you want to run at the same time. It's like saying, I have 1,000 files to process, but I only want 10 workers running at any given moment. It's incredibly powerful.
But I really want to zoom in on index jobs for a second, because honestly, these are a total game changer. Imagine you have a dataset split into 100 different chunks. With an index job, Kubernetes automatically starts up your pods and injects a special environment variable into each one, telling it its unique number, its index. So pod number 5 just knows it's responsible for processing chunk number 5. For so many common cases, this completely eliminates the need to set up a complicated message queue. It's amazing.
So, we can run tasks, we can run them in parallel, but who wants to kick them off manually every single time? Nobody. That's where we move from manual work to true automation. Let's talk cron jobs. And that's where the cron job comes in. It's basically a job template with an alarm clock attached. You define exactly what the job should do, you tell it when to run using a cron schedule, and the cron job controller handles the rest. It's your very own distributed cloud-native scheduler. Now, the schedule itself is just standard cron syntax, which you probably know. But let me tell you, the real lifesaver here, the thing that will save you from getting paged in the middle of the night, is the time zone field. You can set a specific time zone and your jobs will run at the correct local time, even through daylight saving changes. No more weird off by 1 hour errors. It's a huge operational win.
So this leads to a classic problem, a real headache for anyone who's ever managed scheduled tasks. Overlap. What happens when it's time to start the next run of a job, but the last one is still chugging along? You don't want them to step on each other's toes. Thankfully, Kubernetes gives us direct control over this exact scenario. And your answer to that problem is the concurrency policy. Now, the default is allow, which can be dangerous, but the two you'll use most are forbid and replace. Forbid is simple. If the old job is still running, just skip this new run. Perfect for a database backup where you absolutely cannot have two running at once. Replace is more aggressive. It says that old job is stale, kill it, and start the new one right away. This is great for things like warming a cache, where only the latest run matters.
Okay, so we're getting pretty good at creating and scheduling jobs. But now we have to put on our operations hat. How do we build systems that can handle failure, and just as importantly, how do we keep them from drowning our cluster in old completed junk?
So, when one of your job's pods fails, Kubernetes doesn't just throw its hands up and quit. Nope. By default, it'll try again up to 6 times, but it does it smartly. It uses what's called exponential backoff. The delay between retries gets longer each time, 10 seconds, then 20, then 40. This is absolutely critical. It prevents a rapidly failing job from hammering a broken downstream service and gives things a chance to recover.
But what about a sneakier problem? What if the job doesn't fail? It just hangs. It gets stuck. That's where active deadline seconds is your best friend. It's a hard timeout for the entire job. It doesn't care how many retries you have left. As you can see here, once that deadline is hit, Kubernetes steps in, terminates everything, and marks the job as failed. It is your ultimate safety net against zombie processes. All right, now this is where we really level up our game. The pod failure policy lets us teach Kubernetes the difference between different kinds of failures. With the fail job action, we can say, hey, if you see this specific error code for invalid configuration, don't even bother retrying, just fail immediately. Or even better, with the ignore action, we can say, if this pod died because a spot instance was reclaimed, don't count that against my retry limit. That wasn't my application's fault. This is how you build truly resilient, self-healing systems.
Think about it. A busy cluster could be spitting out thousands of completed jobs every single day. If you keep all those old job and pod objects around, you'll eventually slow down your whole cluster. So we have 2 fantastic tools for automatic cleanup. For CronJobs, you can set history limits to say, only keep the last 3 successful runs. And for any job, you can set a TTL seconds after finished, a time to live, which is basically a self-destruct timer that cleans up the job after it's done. This is non-negotiable for good cluster hygiene.
Okay, let's do some quick-fire troubleshooting, the stuff you're going to see in the real world. If you see backoffLimit exceeded, that's on your application. Your code failed over and over. Go check the logs of the failed pods. If you get an event saying too many missed schedules, it means your controller was probably down for a while. You can set starting deadline seconds to give it a chance to catch up. And if your pods are just stuck in container creating forever, that's almost always a resource quota problem or a storage volume that's locked.
So, what's the big picture here? What's the takeaway? Mastering jobs in CronJobs really unlocks the other half of what Kubernetes can do. It's not just a platform for services that run forever. It is a truly universal control plane that can orchestrate any kind of work. So the real question to leave you with is, now that you have the tools to manage tasks that both start and stop, how are you going to unify all of your different workloads on this one amazing platform?